What's up, everyone? Yeah, so this video is going to be like a summary of what was discussed in the blog, and we also try and solidify understanding of the concepts we walked through in the blog. So basically, what we are trying to do is that we are trying to emulate like the behavior of a file system from a very foundational level. So if you want to emulate the behavior of a file system, we have to have some kind of storage, right? And we don't really have access to a physical disk. So what we do is that we emulate the disk as a bin file, right? It's going to be emulated as a bin file. So first let's just talk about the disk. So a disk is like a form of permanent storage device, right? And this is actually divided up into sectors, right? So the first set of this disk, which actually sector 0, um, contains the master boot record and its partition table. So this is what we have here: master boot and its partition table. So this partition table keeps tracks of the rest of the partitions of the disk, right? So all these partitions you are seeing here are made up of sectors too. So you can have, let's say, probably from let's say sector, let's say 2 to maybe sector 4, 5, 7, right? This could be made of it, right? And partition is actually way larger than that. This is just an example, right? So this partition could be like, for example, let's say 30 gig. This could be like 100 gig. This could be like, let's say 40 gig, depending on this disk size. So the MPL keeps track of each partition in the disk, right? So the first partition could contain a, should I say, could be bootable, right? The first partition could be bootable, right? To contain a operating system that is present there. So for example, partition 1 could contain Linux and its file system ext. Partition 2 could contain Windows and its file system, probably NTFS. And partition 3 could contain some other OS and its file system. So yeah, that's how it is. So each partition, if you narrow it down, this is the format of each partition. So we have the boot block, we have super block, we have free space management, inode, root directory, files, and directories. So I'll explain this very soon. So and all the time, it's not compulsory partition could be bootable. Sometimes some partitions might not really have an OS and a file system attached to it, right? It could just be sometimes a swap space, right, or just disk space. But we for this video, we assume that each partition contains a operating system and a file system. So if the partition contains an operating system and a file system, to surely have a boot block. So this boot block will contain a kind of secondary bootloader that actually that contains the booting process. So the first one that first starts is the MBR. So the BIOS switches the MBR into memory, right? And its code is executed. Once its code is executed, his work is to actually track the active partition, right? The active partition is the one that we set, right? Maybe through BIOS, right? Through the order of our BIOS. And that active partition will contain a bootable block, and that also contain a secondary bootloader that will actually try and maybe mount the operating system further and actually mount its file system too. So I think that's what the boot block does. Then next block is the super block. So super block contains information about our file system. Yeah, that was super block contains. So it contains information like the magic number. The magic number. So you can just take this as a form of like a special signature that our file system has to actually like identify the file system. So it's just a special signature. Special signature. So it's a special signature that we use to identify our file system. Then the super block contain other fields like the number of inodes we have in our file system, the number of blocks, total number of blocks we have. It could also contain fields like the location of our free space management data structures, right? It could also contain several other things too, right? It contain the location of the super block itself and several other things. So the super block just gives us information about our file system. So Next we have is free space management. Our free space management is a form of it's a way to actually track should I say all the blocks in our file system. So there are different methods you can use for free space management. The first one is contiguous allocation, right? That's just like we are kind of should I say allocating um should I say disk blocks like consecutively, right? That's it. So we have a contextual allocation, and it's actually easy to read. It's actually easy to implement because once we know the address of the first block, we can actually get to whatever block we want, right? Once we know the address of the first block and the size of the entire disk, we can actually get whatever address we want just by simple addition of offsets. But the downside to that is that for contextual block allocation is that we can have things like fragmentation, right? So once, for example, now we want to like let's say track the um disk blocks, right, that are located to files. Let's say for example a file takes about, let's say, 6 blocks, the next file takes about 4 blocks, the next file takes about 10 blocks, and let's say we now need extra, like let's say we need like let's say 11 blocks, for example. If we remove like file A which takes 6 blocks and file A which takes 10 blocks, or let's say we need like 10 blocks rather, and remove like file A which takes 6 blocks and file B C which takes 11 blocks, we might not be able to allocate the one that we request for 10 blocks because they're actually contiguously allocated. So we have things like fragmentation. I will explain this better like visually. Right, so what you can also have to know is that for free space management using contiguous allocation, we have fragmentation, which is not actually good. Then another method of free space management is linked list, right? So we have like each data block, we have like should I say pointers to the next data block, so you can actually track all the blocks like in the file system. Then the one that is commonly used is inodes, right? So we use inodes to actually track our file system. So another one that is also used is the bitmap, right? We use bitmaps to also track our using. So what we're using in our file system, our implementation is the bitmaps, right? So I try to track all the blocks of the file system. So we have 2 bitmaps. So let me just save that for later. That's for our own file system implementation. So this is just a standard one. Then next we have inodes. So inodes are just like internal manifestation of our files or directories, right? So that's what we call inodes, the internal manifestation of our files or directories. So for example, if we perform a read write, for example, probably in C, like make a Unix code to read write, you have returned a file descriptor, and that file descriptor is like an index into a file descriptor table that contains a pointer to a inode struct representing the file you are trying to read from or write to. So that's what I know. So inodes are just internal representation of files and directories. So this boot directory, I see it as so this is a block too. I see it as a directory entry, right? So this is what I call it. So the root directory is actually an inode and it is found in this inode, but it contains its data blocks is actually represented as a directory entry. So it contains directory entry. I'll explain that very soon. Then we also have files and directories, and these are actually just random data blocks for files. So that's just like a simple overview of a sample file system disk layout, right? So for our own file system disk layout, right, emulated disk layout, so it's just a bin file. We have we're going to strip down a lot of things. So we're going to remove our boot block. We don't really need that for a simple file system for now. And there's going to be some rearrangement into like the structure of our disk layout, right? So first thing is that for our file system, we have our super block. And I've explained that super block will contain things like magic number, which is just a special signature. It will contain things like number of inodes, right? Number of inodes. I'll explain the number of inodes we have here. We have number of inode blocks. Things like location of bitmaps, right? So what we're using to actually track all the blocks in our disk or file system is actually bitmaps, right? So I'll explain that too. Then what is again? I think that's basically all. And maybe I might be skipping something sharp, but when we start looking at the implementation of the code, we'll try to go through it again. So This is the magic number special signature just to identify the file system. Then super block contains all this. Then next after the super block, right? So super block contains a struct, right? A struct super block, which is just 16 bytes, and that's what is just stored in the super block, right? So it just gives us this information. Then after the super block, we have the inode blocks. So inode blocks range from block 1 to block 410. So we have inode block 1, inode block 2, inode block 3, and up to 410. And each of those blocks store inodes. So I'll also come back to that too. Then these are FS bitmap block, and this is what actually stores our free management, free space management, should I say free space management data structures. So FS bitmap block stores our file system bitmap, right? And inode bitmap blocks this plural stores our inode bitmaps, right? So we'll come back to that, and we have indirect block and we have data block. Inode blocks, let's go over this inode block. So inode block is from block 1 to 410. Usually we allocate 10% of the disks to inode blocks. So 10% of the disks are actually allocated to inode blocks. So each of these blocks store inodes. So say our inode is like 32 bytes. Say our inode is 32 bytes. And each block is about 496 bytes, or about 4 KB. So let me just write this. Inode with 32 bytes. Each inode is 32 bytes, and each inode block, or each block in the file system in general, is about 4 KB, and that's about 496 bytes. So if each block is 496 bytes, meaning that inode block 1 will be 496 bytes, inode block 2 will be 496 bytes, inode block 3 will be 496 bytes, and so on up to inode block 10, 410 rather. So each inode is 32 bytes, meaning that number of inodes that a block can store is about 128 by 28 inodes. So each inode block will store 128 inodes. So 128 inodes, right? So if we have 128 inodes for each block, and we have 410 blocks, right? So meaning that we're going to have about, I think this goes to approximately 52,480 inodes. So from block 1 to 10, we house about 52,480 inodes. So number of inodes in our file system that the super block will keep track of is 52,480, right? The number of inode blocks, know that is 410. Then location of bitmap, right? So location of bitmap to be we have 411, 412, 413, right? So the 411 represent our FS bitmap block, right? And 412 and 13 represent our inode bitmap block. So let's explain this FS bitmap block. FS bitmap block is just essentially contains our file system bitmap, and our file system bitmap is just an array. It's an array that just an array that keeps tracks of those. So let me just, a bitmap is a data structure that keeps track of the state of an object. So in this case, we are keeping track of the state of our disk blocks, right? So is it allocated or free? That's what the bitmap does. So to represent each block, to represent the state of each block, we store either zeros or ones, right? So zeros or ones, and we have about 496 blocks, right? I forgot to say that the size of our entire disk is about 4 MB. So if each block is 496 bytes or 4 KB, we have about 496 blocks in the disk, right? So this super block also stores the total number of blocks in disk. Total number of blocks in disk. So it's about 496 blocks in total, right? Number of blocks, right? So and to calculate the total size of the disk, you know that each block is about 496 bytes from here, right? So if you want to calculate the total number of blocks and total size of the disk, rather, we have 496 times 496. That will give us what, about 16 MB if you calculate it, right? 16 MB, right? So that would be total size of the disk 60 MB, and total number of blocks will be 496 blocks, and total size will be 60 MB, right? Yeah, so we are tracking, we want to track about 496 blocks, which is number of blocks in the disk. So we need about 496 should I say bits, right, to track our blocks, right? So we need 496 bits, and the lowest lowest data type we have is C. I'm working with C for this file system. The lowest data type we have is in C. It's a character data type, and the character is a byte, right? So if you want to track each block, right, we don't want to use a byte to track each block, we want to use bits rather, so our bitmap will be smaller, right? So we want to track each block, right, and a byte contains 8 bits, right? So each byte will contain 8 bits. This is I think this is 8. 1 2 3 4 5 6 7 8 is 7 8, and something like this. And so on, right? So this first part is a byte, right, and which is going to store information about blocks. This is another byte too, and this is another byte, and so on until you get to the 512 bytes, right? So this is byte 0, byte 0, byte 1, byte 2, and so on, right? So byte 0 will contain 8 bits, right, and these 8 bits are going to track specific blocks of the disk. So the first bit will obviously track our super block, right? So to track whether our super block is allocated or free, right? By default, our super block, when we are trying to format the system, will actually be allocated, so we give it a 0, right? So 0 means allocated and 1 means free. So next is our inode blocks, right? So we're going to start at inode block 1. Inode block 1 is going to be allocated to by default, right? Because we have actually allocated those blocks for inodes. Then the next block is inode block 2, also going to be allocated up to 410. So up to 410, we're going to have all these blocks to be 0, right? Up to 410, we're going to have all these blocks to be 0. Take out. So up to 410, we're going to have all these blocks. So all these blocks also be 0 up to 410. The FS bitmap block to also be allocated. Inode bitmap block also be allocated. So what essentially what this bitmap block is doing is that it's tracking all the blocks in our disk, and actually it's just tracking the state of the blocks in our disk, right? So all this, right, from super block to inode block to the FS bitmap block itself, to the inode bitmap block, and to the indirect blocks, all these will be allocated, right? Will be allocated, while the tab blocks will be left as free. That is from block 415 to 495, 4095 rather. We have our bitmap to store 1, meaning free. So that's what the FS bitmap does. The inode bitmap spans 2 blocks, right? Because we have up to like 2489 nodes, and a block is about 496 bytes. So if a block is about 496 bytes, the number of bits we can track is this times 8, right? Times 8, and this will be about 32,000 and something, probably 32,000. So we can track above 32,000 blocks for 32,000 blocks, 32,000 inodes rather for each block, right? So you can track about 32,000 inodes for the first block, that's 412, and the next block 413 will track about extra, like out of that's 32,000, we have like 90,000 to track the next block. So so that's what this inode block does. Then the indirect block is like attached to our inode, and it's actually like a pointer to data blocks, right? So it stores data blocks, right? The address, all the data blocks. So if our disk was to be very, very large, we are going to make sure this indirect block. But for now, our disk is small. It's just 60 MB in size. So each inode direct field rather, can should I say can contain all these data blocks, right? Can contain all the data blocks. So this is just like a simple overview of file system disk layout. It might not be clear now, but once we start reviewing the code, you might start getting insight into how this is actually done. And you can also like try and also read through some blogs, articles, and other stuff to try and understand disk layout to an extent. So once we start reviewing code, the implementation of our file system, you might actually get it. So that's all for this video. Thanks for watching.